Let the curve y is equal to f of x be a differentiable real function on the interval I. Consider a point P, x, y on the curve, and a point Q close to point P such that its coordinates are x plus delta x, y plus delta y. Here, delta x is a small increment in x and delta y is the increment in y corresponding to the increment in x. From the figure, y plus delta y is equal to f of x plus delta x and y is equal to f of x. This gives us delta y is equal to f of x plus delta x minus f of x. Dividing both the sides by delta x, we get the equation as shown. Denote this by equation 1. Assume that limit of delta y upon delta x exists as delta x tends to 0. So, applying limits on both the sides of equation 1, we get limit of delta y upon delta x as delta x tends to 0 is equal to limit of f of x plus delta x minus f of x whole divided by delta x as delta x tends to 0 using first principles. The right-hand side of the equation can be written as dy upon dx. Therefore, limiting value of delta y upon delta x is dy upon dx. Hence, delta y upon delta x is equal to dy upon dx plus epsilon, where epsilon is a small positive quantity. Multiplying both the sides by delta x, we get delta y is equal to dy upon dx into delta x plus epsilon into delta x. Since the values of epsilon and delta x are very small, the product of these two quantities is negligible. Hence, the approximate value of delta y is dy upon dx into delta x. That is, the increment delta y in the dependent variable y is approximately equal to dy upon dx multiplied by delta x. We have f of x plus delta x is equal to delta y plus f of x. The approximate value of the function is equal to the sum of the approximate increment value in the function f of x. The differential of the dependent variable, that is dy, is approximately equal to its increment, that is delta y. The differential of the independent variable, that is dx, is equal to its small increment, that is delta x.